Hey, it's Dr. J. This is section 4.6, Math 12, of course, part 3. There's a test Tuesday. Just a reminder, April 14th. So keep in mind this may be on the test. This is the last section before the test. Right, so we're going to sum up the exponential growth and decay. So we'll start with a problem that we've done before. We've done something similar to this before, but this time we'll take a slightly different approach. So we'll start with an example of exponential growth. An initial sample of bacteria. We did a bacteria growth problem earlier, but contains 300 cells. After 40 minutes, sample had grown to 400 cells. Find the doubling time. Doubling period. That's the amount of time required to double the population. Whatever it happens to be. Okay. So, 300 cells to 400 cells. We're going to use our exponential growth model. This is our growth model. The amount is equal to the original amount, the initial amount. That's our C, our initial amount. A is the future amount. And T is the amount of time, 40 minutes. So, 400 cells, that's our A. Started with 300 cells. We don't know the base, that's our unknown. And it took 40 minutes. Now keep in mind, I'm committing now, T is now minutes. All right, so I've made my choice. Had I chosen to do hours, then T would not be 40. We'd have to then convert that. So we decided to do minutes. We might change our mind later. It's probably a bad idea. Divide both sides by 300. And we get 4/3 is a to the 40th. Or in other words, words, the 40th root of 4/3 is equal to A. Here, let me do it. I'll do the whole thing out. Those are going to cancel, and you're going to get A. I'm not sure how well you can see this, but I'll do my best to illustrate. So that's the 40th root of 4/3, which is 1.0072977. There's our A. So now our growth model looks like this. 300 cells times A to the T. This does not tell us the doubling period. This gives us a model that we can use to find the doubling period. I'm all out of space though, so we're going to have to erase a little bit. So use this to find the doubling period. Turns out that it does not matter that this is 300. I'm only putting the 300 because that's what was given in the problem as our constant. We'll see in a second that this constant will become insignificant in a moment. What really matters is the word doubling. I say that because you probably won't have this value of 300. You might have some other value. So I just took my model and I rewrote it over here. And plugging in my A, 1.007217977. Make sure I wrote it down correctly. Looks good. Doubling now. So we want to double. So that'll be 600. That's because it's double. Double 300. And this is where you see that the 300 really doesn't matter because you're about to divide by it anyway, and you will always get a 2. If you're solving a doubling problem. What really matters is this base A. So in the future, when you do this problem, you can jump next time if you know. You can skip all these steps because you already know that if it says doubling, then here's your brain, and your brain says doubling. It's supposed to say doubling anyway. All right, back to the problem. So our goal is to solve for t. That's what we're solving for. So we have take the ln of both sides, just like we've been doing since we learned the technique. Bring your t down as the coefficient. So now it becomes multiplication. And now it's time to break out the calculator. So with our calculator, we've got a 1.007217977. If you're smart, or if you're clever, or if you're not, you might just put that on your, leave that on your calculator. So that becomes t times 0.00719252. And then for the left-hand side, you've got the ln of 2, which at this point you've probably just got memorized if you've been doing your homework. It comes up quite a bit. 0.693147,181. All right. So now we're going to take this, bring it up here, and we get t is equal to 0.693147,181 divided by 0.00719252. Be careful with the zeros. I've screwed this up before. And I get 96.376. We'll go to 4 decimal places. And this is minutes. If they were going to round, if we're instructed to round, I would probably round to the nearest minute. So that would be about 96 minutes. If it tells you to keep it as a decimal, keep it as a decimal. I personally would probably ask you to round it to 96 minutes. So this is the doubling period, also known as the doubling time. Okay. So before we dispose of this, I want to make something clear, that we have different types of models here. So just a discussion about different models. The first one that we had was the sort of algebraic model. A equals CAT. I'm giving it that name because we found this model algebraically. So our model basically said that we had 300 cells. Our base was 1.0072. I'm going to round for this particular explanation because at this point we already have our answer, so I can throw away all these extra decimals because I'm done using this formula now. I'm just going to talk about it for a little while. So this is the algebraic model that we just found. It's hourly. I mean, not hourly. Per minute. Per minute. So this is per minute. You can think of the base A as 1 plus the per minute growth rate. So the base A is equal to 1 plus R, so that's 1 plus 0.0072. So that means that our R here is 0.0072, or 0.7 of a percent, or 72/100ths%, less than 1%. So that's the per minute growth rate. You take your base. Your base is 1 point, whatever it happens to be in this case, 1.0072. It's 1 plus the growth rate, so obviously the growth rate is 0.0072. So that's our per minute algebraic model. We also have what's called our doubling model. The doubling model is the amount that we're going to have is going to be a multiple of 2. But the time is going to change, because the time is not per minute. The time is per 96 minutes. So it's almost like you're treating 96 minutes like that's 1 unit of time. So your model would look like this. It's still A. A is, the amount, or however much you have. We're still starting with 300. But our base is now 2. And every 96 minutes, this will act like 1. So that would be T over 96 minutes. Let me erase. Those are getting a little too close for comfort here. So per 96 minutes. So we're going to divide by 96 minutes. So this has base 2, because it's the doubling model. Base 2 you can think of as 1 plus R. And so that means that our R is 1, which is 100% growth per 96 minutes. So every 96 minutes, this model is doubling its value. Now these have some pros and cons. What's nice about the algebraic model? Well, what's nice about it is look at your power. Your power is super easy. Oh, I almost left it out. It's so easy I almost left it out. It's a T right here. Your power in this model is just a simple T. It's per minute. So if you want to know 15 minutes, you plug in 15. You want to know 170 minutes, you plug in 170. So this model is really easy because you just plug in a simple number. This model, what's easy about it is the base. Look at the base. The base is easy, but now look at the price you pay. Now you don't have an easy exponent. Every time you want to plug in a value, you got to divide it by 96, because your unit of time is not based on minutes, it's based on every 96 minutes. So it's treating 96 minutes as if that's 1 cycle or 1 unit. Finally, you have your third model, your natural model. Now the natural model is base E. So we still have the original amount, 300. Now our base is E, and we need to figure out what K is. Find K. So we look at these. We can compare these two. Our doubling model and our natural model. You might as well just ignore the 300s. We're just going to set these equal to each other. Okay. And go ahead and set t equal to 1, just to be able to eliminate the variable t. Because if we know what happens after 1 minute, then we can certainly figure out all the other values later. So we're simply trying to find k, so we can just set t equal to 1. That makes our equation much easier to solve. We don't want to solve two variables at the same time. Okay. And now we're going to take the ln of both sides. Bring our exponents down. We get 1 over 96 times the ln of 2. You know that the ln of e is 1. So I'm just going to cross it off. You know that that's 1. Technically, that's k times 1. And now you have ln of 2 over 96. So you have a nice formula for k. You might as well memorize it. It'll come back later. This is called the doubling time, the doubling constant. If the doubling time, the period is 96 minutes. So in other words, it's always going to be, your constant is always ln of 2 divided by the doubling time. ln of 2. Oh, can you even see that up there? Probably not. Your k is always ln of 2 divided by the doubling time. Or the doubling period. Okay, so what is that? We have k is ln of 2. Divided by 96. So in this case, k is 0.0072. Oh, interesting. It's almost so you have A is 300 e to the 0.00720283 t. So this is our natural model. It's not a 100% coincidence that these are similar. They usually are similar, but they're actually not identical. If you remember, I rounded this point. This is 0072. This one's unrounded. We could go back and remember where that came from. It was 4/3. And then it was the ln. Four-thirds ln, and then it was the 96th root of that. So it was, no, it was the 40th root. 40th root. No, that's not right. Yeah, anyway. These two values look identical, but they're really not. If we go back and look, the decimals were slightly different. So let's finish the summary, and I'll not get hung up on the little details like that. Make sure that you know this formula. If you know the doubling period, it's ln of 2 divided by the doubling period. That gives you the natural model. That gives you an easy way of finding k. Yeah. Using this formula here to find k. This k value is usually very similar to the growth rate over here. But again, that's just a coincidence. In this particular case, it's a per minute growth rate. This is a continuous growth rate. So that would be 0.72%. So the continuous growth rate and the per minute growth rate are very, very close. That's because a minute is not a very long period of time. So if you were to measure something every minute, its growth rate is very close to continuous. If I were measuring this every day instead of per minute, if I were measuring it every hour or every day or even every year, then these rates would differ greatly. But because a minute is a small amount of time, very close to the per minute rate. Okay. So in conclusion, you now have 3 different models for the same problem. I do not always need all 3 models. I just want you to see that there are 3 different ways of thinking about the same problem. So this particular situation has the 3 different ways. All of the situations will have 3 different ways of looking at it. Okay. All right. I think we've had enough of that. Next, we're going to talk about decay. An initial sample of a radioactive substance contains, or has a volume, I should say. I'll say mass. 300 milligrams. After 15 hours, the mass has decayed to 150 milligrams. Find a base E model that gives the mass, the substance, terms of t, the number of hours since this experiment began. All right, ask the question. I'm also going to ask a supplemental question to use the model to predict the mass after 24 hours or 1 day. Okay. So, starting with 300, after 15 hours, we have t is 15. Our initial amount we'll call A, and then actually let's call our initial amount M0, and then we'll call this MT. So we have and we're using base E. This subscript notation will be useful. This means mass at time t, and this means mass at time t equals 0. So the subscript notation is convenient for this type of problem. I could use the old A and C or other variables that we've seen in the past, but I'm trying to adapt my formula to the current situation. Okay, and then we have our time is 15 hours. So we'll go ahead and plug everybody into this relationship here. So we have 150 equals 300 e to the k times 15. Now in the next step, it's always the same second step after you set up the model. You're always going to divide by whatever your constant or whatever your initial amount is. That's this M0 is this initial amount here. So that teaches us a lesson, a very important lesson, that these values really don't matter all that much, because this fraction is what really matters. If this is a half, then this is called the half-life. Okay? Only if this value comes out to be exactly a half, if these values are 1/2, their ratio is 1/2, then this will always come out to be 1/2 or 0.5. Okay, then we're going to take the ln of both sides. You know what to do next. The ln and the e are going to become 1. Become 1. The 15k is going to come down. You're going to have ln of a half equals 15k. You're going to divide both sides by 15. You're just walking the dog now. You've done all the hard math by the time you got to this point. If you made it this far, you're home free. Okay. I'm going to write that a little bit more legibly. ln of 0.5 divided by 15, and that's going to be your K. So what do we got here? We got 0.5 ln divided by 15. So K is negative 0.04621. I know I usually go to 4 decimals, but for this I'm just doing 5. Follow the instructions, whatever it happens to say. Okay, so we get a nice formula out of this example. We get this formula here, the half-life formula. So, formulas to remember. We'll call these useful formulas. So we have MT is M initial e to the KT. If you know the half-life, say H is equal to H, then K is equal to ln of 0.5 divided by H. Okay. Oh, this is for decay. Might as well go for it. Let's use NT for number. So this is our growth formula. If you know the doubling time, say D, then K is ln of 2 over D. That would be your growth. And these are both called the natural decay and growth functions. Okay.